Team 2021 would like to present our project called Mobile Handheld Tissue Compression Tester. Our sponsor Medtronic already has a surgical stapler that combines 3 complex steps into one easy step, which is compression, sealing, and cutting. At first, the stapler will compress the tissue that will be operated on, and then it would apply 3 sets of staples on the left and the right side of the stapler, leaving a gap in the middle for the incision. Then, the final step would be to cut the tissue. However, organs are made up of different tissues and they're made up of different properties. Therefore, there can't be a one-fits-all stapling method. So, the stapling method needs to vary. This is even more crucial when operating on unhealthy tissue, which is why Medtronic has given us the task to create a handheld device that would collect stress data on tissue, and this data would then be used in order to make changes to the stapler to improve the outcome of it. This is the schematic of the device overall. As you can see, the device is being powered by a 12-volt battery that then leads into the speed controller and a 3.3 voltage regulator. This 3.3 voltage regulator then powers the Arduino. Going back to the speed controller, this is connected to both the Arduino and the motor/encoder. Another important part of this device is a load cell, which is connected to an analog digital converter, which then leads into the Arduino. The device also has a voltage divider that is connected to the battery and the Arduino, which can detect the battery condition and light up the LED when needed to charge the device. There are also 3 switches on this device, one to turn on and off the device, another switch that will activate the main code and set the compression of the tissue, and lastly a toggle switch that can change the speed of the compression, varying in 3 different speeds.
I have the motor with encoder feedback, motor driver development board, and Arduino Nano 33 IoT microcontroller, which will be connected to the computer through a USB. I have 12 volts going to the motor, 5 volts going into the encoder, and ground, and that's coming from the power supply. I use the PID library in Arduino to control the speed, and for position control, I set 3 zones for limiting motor speed depending on distance from target position. And now I'm going to run the code. The resulting graph shows that the motor settles at 30 radians, which was its target position. The vertical axis is the motor position in radians, and the horizontal axis is the number of samples with a sample time of 10 milliseconds. The graph shows the speed response of the motor with 3 speed zones before settling down to 0. The vertical axis is the motor speed in radians per second, and the horizontal axis is the number of samples with a sample time of 10 milliseconds.
When the device is started, the top of the clamp will descend onto the tissue, compressing it into the load cells. The force being applied to the load cells until a certain displacement is reached is what is recorded. Circled are the 2 load cells that will be used to get the data. 2 load cells are necessary in order to be able to record the maximum amount of force applied to the load cells. The load cells are connected to the HX711 load cell amplifier. This is used to convert the data from the load cells into output values. The load cell amplifiers are connected to the Arduino development board, which will use Bluetooth to send the data over to the computer, which will be storing the data in. The data retrieval and transfer is implemented by the code shown. This is an example of how the data recorded will be organized. Since we are recording data in real time, this column will show when each sample was taken. This column will show how many samples are taken until the desired displacement is reached. This column will show how much force in pounds is applied to the load cells at each sample, and this column will show the sampling rate. Due to the pandemic the world is going through, changes were made to the project schedule. Parts were distributed based off of each member's specific task. Since certain parts were needed for more than one task, orders needed to be made, causing delays due to shipping delays. Since we were not on campus, we could not all meet to troubleshoot together. This required for better communication between each other, the ME team, and the sponsors at Medtronic so we could complete our tasks to the best of our ability.
Once the device is fully assembled and functioning, a potential future step would be to add a display onto it to show different options for changing settings and making it more user-friendly. We would like to thank Medtronic for sponsoring our project, Matthew Eschbach and Robert Neff for being wonderful mentors, Dr. Detta for being our advisor, and the University of Connecticut for giving us an opportunity to apply our critical thinking skills to solve a challenging problem and make a positive contribution to the medical industry.